Alright, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for this session. What we're doing here at OneClass is we're going through this process of verifying solutions for frequently asked problems in mathematics and in chemistry. So what we have here is at OneClass is we group together a bunch of questions in both mathematics and chemistry in the secondary school level as well as in the college and university level. And what I'm doing now is I'm verifying these solutions. So I'm going to go through, so in this live stream of about an hour, I'm going to go through some of these frequently asked problems and I'm going to answer those questions. So hopefully you viewers at home or you students at home will be able to kind of walk through that process with me as well. I'll be able to teach you that concept through the question, and you'll be able to have the best solutions moving forward. Again, my name is Joey. I'm currently a secondary school teacher in Ontario and a teacher at OneClass, and my subjects of interest are chemistry and mathematics. So without further ado, I have 10 problems for us today, ranging anywhere from grade 9 to about grade 12 chemistry, and I'll be able to answer these questions for you today. So let's get started on today's problems. All right, our first problem here says this. So it says calculate the acid dissociation constant of a weak monoprotic acid if a 0.5 molar solution of this acid gives a hydrogen ion concentration of 0.000001 molar. So how do we do this problem? Well, what we want to do is we want to first write out the chemical equation for this guy here. So it says here we don't have specifically a chemical equation, but we have a weak monoprotic acid. So we can assume that we have some type of HA here, and it's going to dissociate into its hydronium ion. So we can say HA plus H2O. It's going to be in equilibrium with, and once obviously if you have a weak acid, it's going to dissociate into its hydronium ion, right? So I'm going to lose the hydrogen here and get my conjugate base here. So this here is my my formal chemical equation here. Again, I have HA as the weak monoprotic acid. It's in water as a solution. I'm going to give up one of these. It's going to donate one of these hydrogens to the water to make hydronium ions, which is H plus, and then I have A minus as well as my conjugate base. So what we want to do is we have some type of initial concentration, and we want to calculate the acid dissociation constant. So what is that? Well, that's simply our Ka of our expression, right? That's the Ka of this formula here. So we write down, we want to find out our Ka, right? So in order for us to do that, well, we want to create an ice table because we know this is in equilibrium. We have our initial concentration, so we're going to create an ice table. And let's write down our ice table. And what we have is, ice table stands for initial concentration in equilibrium. Well, we have a 0.5 molar of solution of acid here. So we can say that initially, the concentration of our weak monoprotic acid is 0.5 molars. So we can write 0.5. We don't care about the water in this case here. The water, we can kind of X out that entire column because water here is in our solution, and water is a special. You can think of it as a special compound that doesn't contribute to my equilibrium constant here. And if we're starting initially, obviously we have 0 hydronium ions and 0 conjugate base, right? And then and then when we do our change in equilibrium, we're going to get some type of minus X here, and then we're gonna get plus X and plus X as well. I'm gonna gain product, I'm gonna lose some reactants, right? So hence why this is the minus sign, and hence why this is the positive sign. And at equilibrium, I'm gonna have 0.5 minus X, and have positive X here and plus X here. And now what we can do is we can actually set up our Ka expression, right? We can say our Ka is simply equal to our products, concentration of products over our reactants, right? So we can say we have H3O plus times A minus here, divided by HA. And the reason, again, why we don't put water as our concentration here is because water here is in liquid form, and it does not contribute to our equilibrium expression. So do we have the tools to solve this? Well, we do, right? Because it gives us 0.5 solution of our acid, but it also gives us a hydrogen ion concentration of 0.0001, which means our concentration of the hydronium ion is 0.0001. So our X here is going to be 0.0001. So we can say that this guy here is 0.0001 molar, which means if this guy is our x here, this guy has to be also my x as well. So this guy would have to be 0.0001. And then this minus x would be simply whatever 0.5 minus that is, right? So let's write that down. So let's see, so let me substitute these guys first. So hydronium, which is x, times A minus, which is x, divided by HA, which is 0.5 minus x. And then I can say that my x here is going to equal, or the concentration of our hydronium at equilibrium is 0.0001, right? So I can say that my Ka is equal to 0.0001 times 0.0001 divided by 0.5 minus 0.0001. And this here, after I do this math here, it will give us our equilibrium expression for the Ka. So all I'm going to have to do is simply just some calculator work. So let me type that into the calculator for you. So I have 0.00001 squared, because I'm multiplying it by itself. I'm going to get 1.1 times 10 to the 8, negative 8 here, sorry. And then I have 0.5 minus 0.0001. I'm going to get 0.444999. So simply just you can think of it as multiplying by 2 here. So I have 1 times 10 to the 8, or negative 8, sorry, divided by 0.4999. This will give us a value of 2.00 times 10 to the negative 8. And this here is our Ka expression for our answer here. And in terms of significant digits, if we're looking at this guy here, I have 1 significant digit here and 4 here. So I would follow the first guy here, which means our answer specifically should be 2 times 10 to the negative 8. So this here is our answer. And as you can see, this answer matches the given solution. So the solution here is correct. All right, let's do number 2. This is number 1. Number 2 is asking, enter the IUPAC name of the ester depicted below. So I'm going to redraw this ester for us here. Okay, it's asking us what is the IUPAC name of this guy here. So whenever we're naming organic compounds, we have to follow some specific rules for naming our organic compounds. We want to first find the longest chain, and we want to find which functional group has the highest priority. So in this case here, this question actually gives us a very, very massive hint. And it says here that it entered the IUPAC name of the ester. So we know for a fact here is an ester. And we know that because we have the C double bond O here. And this here is the ester group. So it's very, very, very obvious that we want to prioritize this group as well. So given that this here is an ester group, what we can do is we can start naming some carbonates, right? So again, we want to say that we want to prioritize this guy here, which is our ester group. So we can say our longest chain is going to be 1, 2, 3, and 4, right? So we have a longest chain of 4 here. And then with all ester groups, we also have the other group, which is the alcohol group, right? So you can think of it as ester as a carboxylic group reacted with a alcohol, right? So this part here is our alcohol, so we need to also number that as well. So this would also go from 1, 2, and 3. And again, this is separate from the this numbering is separate from the ester group because we're prioritizing the ester here. So how do we name this? Well, it's very, very easy now. How do we name our ester? It's our ester. The nomenclature for an ester is in 2 parts. The first part is the alcohol part. The second part is the ester part. So let's name the alcohol first. So this guy here is our alcohol. So we have 1, 2, and 3, which means this guy would be a propyl group, right? So I'm going to say propyl for the first term in our name. So this is going to be propyl. And then again, you leave it as YL here because this is not technically an alcohol. We visualize this as an alcohol, but we follow the same naming as an alkyl group here. So this is a propyl. And then we can name our ester, right? So let's look at for any side chains, some side branches first, and we see that we have a methyl group on 2, right? So this guy here is a methyl group. So we can say that we have 2-methyl, because this methyl group is on 2-methyl. And then we have 1, 2, 3, 4. So the prefix for 4 is butan, or a bute. We have all single bonds, so it's AN. And then finally, the ending for the ester is OATE. So we have 2-propyl, 2-methyl, butanoate. And this here is our IUPAC name for this answer here. And as you can see, they wrote 5-methyl. So they probably started from this other side here. So this is the IUPAC name for the ester depicted. And as you can see, let's see, this is propyl 2-methyl butanoate, which is also the correct answer. So the solution is correct. They even wrote out the mechanism here for this propyl group leaving and you getting an ester here, which is nice as well. So you have some type of R group here. So there's a propyl group, and then you have the butane side main group here. I don't think that was mechanism, but I think they just separated out. So it's good for it's good for the viewers as well. All right, number 3. How many SO3 2- ions are contained in a 99.6 milligrams of Na2SO3. The molar mass of Na2SO3 is 126.05 grams per mole. So we have 99.6 milligrams of Na2SO3. And we want to figure out how many SO3 ions. SO3 2- ions in the sample. Well, the one thing, when we visualize this problem first, we want to see that our units are correct first, right? So we have 99.6 milligrams. So first we want to convert that into grams first, because that's the SI unit for when we're calculating for moles or for molar mass as well. So we want to convert this into grams. So we want to say we have 99.6 milligrams. Multiply that by, it's going to be 1 gram per 1,000 milligrams. So we're simply just dividing this by 1,000, right? So we have 99.6 divided by 1,000. This is going to give us a value of 0.0996 grams. And then what we're doing here is, once we convert it to grams, what we can do is now convert this into moles, right? Because again, we want to find how many ions this is, so we want to convert from grams to moles, and then find the mole ratio, and then convert it into ions, which using Avogadro's number. So we have our mass here, so we want to find our moles. So moles is mass over molar mass, which is simply 0.0996 grams divided by, the question is nice because they give us a molar mass, right? So it's 126.05 grams per mole. And this will give us the moles of our sodium sulfate here. So this is 0.0996 divided by 126.05. That'll give us a value of 7.902. Sorry, 7.902 times 10 to the negative 4 moles, which is exactly what they have here, which is good. So we're on the right track, and they're on the right track as well, except they didn't include the units here, which is unfortunate. So let's see. What we have here is, now we have to find some multimole ratio, right? So we can look back at our compound, which is Na2SO4. Or sorry, Na2SO3. And what we have here is we have Na2SO3 here, and if we want to break this down into its kind of its components here, we have Na plus SO2, or sorry, SO3 2 minus, and we have 2 sodiums here. So if you look at the multimole ratio, sodiums would have 2 moles, or 1 mole of sodium sulfate is equivalent to 1 moles of the sulfate ion, but 1 mole of sodium sulfate is equivalent to 2 moles of sodium here. And again, we're not solving for sodium, we're solving for sulfate here. So this is a 1-to-1 ratio here. If you look at the coefficients, this is a 1-to-1 for Na2SO3 and SO3 2-. If we were asking for sodium, it would actually be a 1-to-2 ratio because there's 2 sodiums on this side to balance out this equation here. So if it's a 1-to-1 ratio, that means we know that we have 7.902 moles of also our sulfate, right? So therefore, we can say we have 7.902 times 10 to the negative 4 moles of SO3 2-, and then all we have to do is multiply that by Avogadro's number to get us our ions, right? So we can say that number of ions, so you can say Na equals moles, or sorry, that's the Avogadro's number. Let me just write this out first for you. So I usually use capital N for number of particles, or number of ions, but it doesn't really matter. It's going to be moles times Na, where Na here is Avogadro's number. So N, again, I have 7.902 times 10 to the negative 4. Multiply by Avogadro's number, which is 6.02 times 10 to the 23. This is moles per, or sorry, this would be ions per mole. And that would make the moles cancel out here. And then you would get your final value of 6.02 times 10 to the 23. You get 4.76 times 10 to the 20, which is exactly the correct answer for this problem. So we have 4.75. Let's see how many, 75, write 757 first. Ions, and then what we want to do is look at our significant digits, right? So we have 3 significant digits here and 5 here, so we would follow these 3 here. So therefore, we have 4.76 times 10 to the 20 ions here. So this is our solution for this problem, and as you can see, the solution is also correct. All right. Let's look at number 4. Number 4 is asking us, what is the formula for ammonium carbonate? Ammonium carbonate. So with this problem, what we want to do is we want to actually separate these guys into kind of 2 compounds. We have ammonium carbonate, so we know this is going to be an ionic compound. So if you do look at your periodic table, you're going to realize that you're not going to actually find anything there, because ammonium and carbonate are both polyatomic ions, which means they're actually compounds that that exist together as one charge. So usually what happens is if you're just introduced this for the first time, you would actually get some type of chart with charges of commonly used polyatomic ions. If you're probably in a higher level chemistry course, you probably wouldn't be given that, and you would be expected to know what these charges are. So if you weren't, I would just give you the breakdown. So ammonium is labeled as NH4 with a charge of 1+. And carbonate is an ion here, and this is CO3 2-. So we have ammonium here, and we have carbonate here, and this is going to form a compound, right? So again, what you can do is you can think of either the crisscross method, or you can think of how do we balance out these charges? Well, again, I have a 1+ charge here and a 2- charge here. I'm going to have to put 2 ammoniums here. I'm going to put 2 ammoniums onto this guy, because I'm going to multiply this by 2, so we had 2+ charge, which balances out this 2- charge, because 2 plus minus 2 equals 0, right? So I'm going to need 2 ammoniums here. So I'm going to think of this as multiplying by 2, which means I have NH4 2, then CO3. And this here is our chemical formula for ammonium carbonate. Or you could have thought of this as crisscrossing the charges here. This guy could go here, so my 2 goes here, and my 1 goes here, so I don't write it out. So any method works in this case here. But ammonium carbonate has a chemical formula for NH4 2 CO3. And as you can see, this solution is also correct. All right, let's do number 5 here. Again, they don't have the solution here, so I might have to calculate this myself. So this is a long question, so let me read this out first. So I have the decomposition of nitramide, O2NNH2 in water has the following chemical equation and rate law. So I'm going to write this down. So O2NNH2 decomposes to form N2O plus, oh, this is a gas, so I'm going to write the states as well, plus H2OL and then the rate. I'm just making sure I'm balancing this correctly. Is this balanced? So I have 2 N's here, which is good. H2, then 1O. Okay, we're good. And then the rate here, oh, sorry. So the rate, I'm going to write as R is equal to, again, O2N and H2 divided by H here. I don't know if it's cut off or something, but because there's no hydrogen gas, no H here. Maybe they meant H2O. I'm not sure what they're writing this by, but I guess I'll just write that down first. So it says a proposed mechanism for this reaction is, oh, so they're actually going to break this out into mechanisms. Okay, that's fine then. So we have K1. Oh, sorry. So we have K1. So we have O2N and H2 plus H. So this guy is a fast reaction. And then we have K2, which is O2NNH, yields N2O plus OH. And this step is slow. And then finally we have K3, which is H plus OH, which gets H2O, which is a fast reaction. So it says, what is the relationship between the observed value of K and the rate constants for the individual steps of the mechanism here? So again, if we look at, if we break this out again, this entire equation breaks down to 1, 2, and 3 chemical equations here, and they actually give us the speeds of this. So for example, K1 here is fast, the rate of this reaction is fast, K2 is slow, and K3 is fast. And we care about the rate determining step, which is this slow step here. So K2 is what we're actually interested in. And we're assuming that K1, K3 go very, very fast. So which means the rate is actually only determined by the slow step here, which is K2. So when we're asking, if it's asking what is the relationship between the observed K, which is, I guess this K here that I forgot to write, and K2, K here would simply be equal to K2 because we assume that K1 and K3 are very fast. So K2 here is the slow guy. So that's what we care about when we talk about our rate of our overall reaction here. So K2 is going to be our answer for this problem. So again, this step is, says here the rate law is determined on the slow step, which is correct. So this is a slow step. Hence, the rate of reaction will be governed by the slow step and the fast equilibrium reaction. So again, we only care about this K2 here. So hence, the correct answer is shown above. Was there a K negative one as well? I'm trying to look at K negative 1. I guess it was this guy here. K1 here doesn't show me a speed for this one here, so I'm not sure about the speed. But again, because they wrote that the slow step here is K2, right? So we're good in saying that the K2 is the is related to this K here in terms of the rate of the overall reaction. So I'm going to say solution is incomplete, but provides correct logic in this specific question. K2 is the rate determining step, so it will also be the rate of the overall reaction. We assume that K1 and K3 are fast steps, and the rate is determined by the slow step. Some of the solution here is correct, but they failed to write down K2 here, but the logic here is correct. All right, let's look at number 6. So this is a generic salt, AB2, has a molar mass of 317 grams per mole and a solubility of 4.00 grams per liter at 25 degrees Celsius. What is the KSP of the salt? So I believe for question 6. Just give me a second here. Yeah, so that's 1, 2, 3, 4, 5. Yeah, we're question 6 here. So AB2. So what I want to do is I want to first figure out, again, the chemical reaction for this one, for the salts here. Right? So I have AB2. So what this is going to break down, so again, this is a salt, so I know it's an ionic compound. So I have some type of cation and anion. It's going to break down into, I'm going to write our equilibrium sign as well. It's going to break down into, again, I have A 2 plus and B 1 minus, right? And then the reason why we know this is because of this coefficient of 2, right? You can think of the reverse crisscross, and you can think of the 2 here used to be the charge of A, and the 1 here used to be the charge of B. So A would have to be 2 plus charge, and B would have to be a minus charge here. And in order for us to balance this equation, I would have to put a 2 here for B here to get to balance out the B's. So again, now I can write the KSP formula for this salt here. So if KSP is going to equal to, again, just the, I'm looking at the concentration of our products, right? So I'm going to have A 2 plus, and then I have, again, B minus here, but we have to include this coefficient, so this is going to be B minus squared here. And because the coefficient of 2 is in the exponent of our concentration in this case here. So what do we have? We have a molar mass of 317 and a solubility of 4.0 grams. So what we want to figure out is we want to figure out the KSP, right? So we want to find out first the concentration of these guys here. So how do we figure out concentration? Well, we have our molar mass here, which is grams per mole. And then we have the solubility, which is 4.00, which is grams per liter, right? And we have grams per liter. And we want to get moles per liter in because that's going to represent our concentration, right? So we have grams per mole and grams per liter. So I'm going to have to divide both of these guys here, right? So grams per mole multiplied by liters per gram. And let's see. That actually might not work out because I get liters per mole, which is actually not correct here. So I would have to do grams per liter first, divided by grams per mole. So I have grams per liters times moles per gram, and this would cancel out to get moles per liter. So this is our equation here. So grams per liter, which is our solubility, and then divided by our molar mass here, which is grams per mole. So let's do this calculation. And again, the reason why I did this is because we're not specifically given a formula for solubility and for molar mass. So we had to actually use this concept of dimensional analysis for us to figure out which units would cancel out to give us moles per liter. And that's why I did this little side work here. So grams per liter, which is 4.00 grams per liter. We're going to divide that by 317 grams per mole. And this will give us moles per liter, right? Because again, these grams will cancel out and the moles will actually come up here. So we have 4 divided by 317 is going to be equal to 0.0126. And then we have moles per liter here, so our concentration. And then what we can do now is we can actually sub this concentration into our KSP formula. So let me just rewrite that for us here. And 0.10126 is going to be our x values here. So we can say that this is 0.0126 multiplied by 0.0126 squared, which is simply just, we have 0. I'm missing a 2 here for our formula here, because again we had the coefficient of a 2 on this side here, so it has to be reflected on our in our KSP formula. So you can think of it as 2s minus here. So I'm going to have a 2 as well. So this is going to be multiplied by 2. That looks really bad. Give me a second. So I'm going to have 2 times 0.0126 squared. And this is going to give us our final answer, right? So we can plug this all into our calculator. Let's see, we have I'm going to do 2 times 0.0126. I'm going to square that, and then we'll multiply again by 0.0126, and I'll give us a value of 8.00 times 10 to the negative 6. This is going to be our KSP value, and as you can see, this is very, very close to this KSP value. So it will give us the correct answer for this problem. So so 8.00 times 10 to the negative 6. So this is the correct answer. And I think they're slightly off. I think they did the math slightly off, or maybe they actually kept more decimals, which is actually probably better in this case. So let me keep a little bit more decimals and see if that changes our answer in terms of rounding. And it would. So they actually they kept more decimal places here, so they actually got 8.4 times 10 to the negative 6. So let me just change this then here to reflect those decimals. So I thought taking 4 decimal places was enough, but I guess it was not. So that was my fault. There we go. So that's what you should plug into your calculator, and then you get a value instead of 8.04 times 10 to the negative 6. And this will be our KSP value for this problem. So this solution is correct. They actually did a better job than I did because I didn't take enough decimal places for the concentration. All right. Let's look at 7. It says name each molecular compound. So we have A, CO. B is we have Ni3. C is SiCl4. D here's N4SE4. So the trick here is molecular compounds, right? We know all of these guys are made up of basically either non-metals and some are metalloids, like silicon here is a metalloid, but it's not an ionic compound. So we don't follow the same rule as for naming ionic compounds. We follow the same nomenclature for molecular compounds. And for molecular compounds, if you remember, we want to always add the prefixes, the mono, the di, the tri, the tetras, and these will help us name these compounds here. So our first guy here, we have CO. So we have our first element here is carbon, so C, which is carbon, and then we have O here, which is usually oxide for an ionic compound, but in a molecular compound we have to add the prefix, right? So it's carbon monoxide because we have one oxygen here, so monoxide. Same thing with the second one. We have N here first. We have nitrogen, and then we have I3. So again, we have iodide for I, but then we have three of them, so you have to put triiodide. Triiodide. I think it might just be one I. Might have misspelled it. Yeah, triiodide. You might have to. I don't know how to spell that, but I think it's like two I's, maybe one I. You'd have to check that for me. Third one here, we have Si, which is silicon. So SILLICON. And then we have Cl4. So Cl here is chlorine, but again, we have four of these guys here. So and the prefix for 4 is tetra. So it's going to be tetrachloride. So silicon tetrachloride. And then finally, for this guy here, we have N4SE4. So we have 4 nitrogens first. So this would be tetranitrogen. Oh, sorry. So tetranitrogen, Se4, this is selenium or selenide. So we can also say, and we have 4 of those guys as well. So we can say tetraselenide. And those are going to be our names for our compounds. So let's check our answer here. So let's see. We have, and again, the formatting makes it so that I actually couldn't figure out the naming. So let me just write down the naming for them. And I'm going to mark this as incorrect because I think it got cut off. Their answers got cut off here. So CO is carbon monoxide. And I3, nitrogen triiodide. I want to say it's 2 I's. Maybe Google will help me out. Nope. I'll leave it as that. Cl4 is silicon tetrachloride. And N4 Se4 is tetranitrogen tetraselenide. So that's going to be our answer to this problem. Let's look at number 8. So if iron is mined from the earth as iron ore, common ores include Fe2O3, hematite, Fe3O4, magnetite, and FeCO3, which is siderite. So calculate the mass percent composition of iron for the first one of these iron ores, calculate the mass percent composition for iron for the second one of these iron ores, and calculate the mass percentage or mass percent composition for the iron for the third one of these iron ores, which ore has the highest iron content. So we want to figure out basically mass percent composition. So let me break this down to A. So A here is Fe2O3. So we have Fe2O3. So this is hematite for our first mass composition. In all of these problems here for mass percent compositions, every time you see a percent here, we need to assume something. In terms of our assumption, we're going to assume our mass here, and we're going to assume that it's going to be 100 grams. And the reason why we assume 100 grams is because it's easier for us to work out the percent of those guys here. So assume we have 100 grams of Fe2O3. So we have, if we assume our mass here, what we can do is actually calculate the moles, right? Because again, we have moles. Moles is equal to mass over molar mass. So we have 100 grams over the molar mass of Fe2O3. So let me find that out for you. And let's bring up our periodic table now, because we're going to need to know that. So Fe2O3, so I have Fe, which is here, so 55.845, multiplied by 2, because we have 2 irons. So we have 2 times 55.845, plus 3 oxygens, which is 3 times, again, oxygen is here, so it's 15.999. And then we can calculate that, use your calculator. So we have 100 divided by 2 times 55.845 plus 3 times 15.999. We're going to get a value of 0.626. So let's check our answer here, which is good. So they have also 0.626. Maybe I'll add more decimals here, 0.6623 moles. And then what we can do now is we can look at our mole to mole ratio, right? We have 0.62623 of this entire compound. However, how many do we have of specifically iron, right? We care about the iron. And again, what we can do is we can actually write out our chemical formula to figure out the mole ratio, right? So we have Fe2O3, so we're going to have Fe3 plus O2, right? And then we can balance this A out by writing a 2 for iron, and you can think of this as 3 over 2 for this guy, or you can think of it as 3 here to give us 6, and this one would give us 2, and this one would give us 4. But again, we don't really care about balancing here. We care about simply just the iron coefficient here, because it's not asking us for oxygen. So we can say it's a 1:2 ratio here. So we're going to have to multiply this mole ratio by 2 to give us our moles of iron. So this is Fe2O3. So we're going to take that, we're going to multiply it by 2. Multiply that by 2 moles of Fe divided by 1 mole 2CO3 or O3, sorry. Then these guys are going to cancel out. So I'm going to get my moles of Fe is going to be 0.62623 multiplied by 2, which is 1.25246. Now what we can do is we can convert this back into our mass and then calculate the mass percentage, right? So we have moles here, want to go back to mass. So if we want to figure that out, we have moles equals mass over molar mass, which means mass is equal to moles times molar mass. So this is going to be equal to 1.25246 moles multiplied by the molar mass of iron, which is what we wrote about, which is what we wrote here, right? 55.845. Moles are going to cancel out, and we're going to be left with grams. So multiply that by 55.845, and we get a value of 69.94. And then what we can do here is we can simply now calculate the mass percent, right? So mass percentage of iron is simply just the mass of this divided by the mass of 100 grams here. So we have 100 grams of Fe2O3. So we can say mass percentage is equal to mass of Fe divided by the mass of Fe2O3. So 69.94 divided by 100 grams. This is going to be equal to 69.94%. And this is our percentage for our first composition. And what we have to do is we have to repeat these steps for the second and third options as well. So this one was the first one, which is actually our correct answer. I think they're off by 0.1, but that might be a rounding error on their part, but that's okay. What I can do is I can actually do the other two as well. just to check their answers. So I have 69.94, which is our first answer, which is good. So Fe2O3 has a 69.94% of Fe. And then I'm going to do the other two. And I'll do this a little bit quicker because it's exactly the same process. So we have Fe3O4 this time, which means we have Fe plus O2. And we're going to have, let's see, we're going to have 3 irons and 2 oxygens here. And we don't really care about the charges that much here, but you can think of this as a 2 minus charge and think of this guy as a 1 plus charge here. So in this case here, we have different multimole ratio, right? So let's calculate. Again, we have to assume our 100 grams. So we want to calculate our moles, right? So moles is 100 grams divided by our molar mass of this guy. So it's 3 times 55.845 plus 4 times 15.999. Put that into your calculator. You get a value of 0.432. You get the multimole ratio. Again, this is per 1 of Fe3O4. So we're going to have to multiply this by 3 to get our iron, right? So let me shift this a little bit here. These two guys cancel out, so we're left with our moles of iron here, which is simply 1.295 or 1.30. All right, 1.296 here for rounding purposes. And then what we can do is, again, we can convert this back into our mass, right? So we have, again, mass is equal to moles times molar mass. So we have 1.296 moles times 55.845 grams per mole. This is going to equal 72.35 or 0.360. And then we can calculate our mass percent, right? So percent is going to equal the mass of our Fe divided by the mass of our Fe3O4, which is 72. Sorry, this isn't percent. This is in grams. 0.360 grams divided by 100 grams times 100%. This is going to give us a value of 72.36%. And this is our second one for this guy here. They wrote 72.4, so they rounded, which is also correct. So Fe, this Fe3O4 has a 72.36% mass of Fe. And then finally, what we can do is we can do the last one here. Very, very tedious, this question, but we almost got it. So we have FeCO3. And again, this you can think of this as a this decomposes to Fe plus either CO3 or CO2, but we don't really care about the carbonate here. And in this case here, we can see that this is a 1-to-1 ratio. So you don't have to worry about converting the mole ratio here. So again, we're assuming 100 grams of FeCO3. So we have moles is going to be mass over molar mass. So we have 100 grams divided by our molar mass of this guy. So it's going to be 55.845 plus the molar mass of carbon, which is 12.00011 plus 3 oxygen. So 3 times 15.999. Plug this all into your calculator. So that's 55. Yeah, this is a 55.845. 0.845. My writing's become messier. Plus 12.011 plus 3 times 15.999. This gives us a value of 0.8632. This is moles of FeCO3. And we said we already assumed that this is a 1-to-1 ratio, so we can also assume that this here is also 0.8632 moles of Fe. So we can convert that back to mass, right? So we have mass is going to equals moles times molar mass. And the molar mass is 55.845 grams per mole. This was a mole. Moles cancel out. Multiply those two numbers, you get 48.20 grams, and then of Fe. And then we get to figure our mass percent is equal to our mass of Fe divided by the mass of our FeCO3, which is 48.20 grams divided by 100 grams times 100%. And this is going to equal 48.20%. So that's going to be our answer for all three of those guys, which or has the highest iron content. Well, again, highest content has the highest percent, which is 72.4. So which means that magnetite has our highest iron percentage. So write this down. FeCO3 has a 48.20% mass of Fe. Therefore, Fe magnetite would have the highest mass percent composition of iron. So the solution is partially correct because they only figured out the first two. So I'm going to say incorrect just to help fix that up. I think I have time for maybe one more problem here, and that's going to be it for this stream because that was a very long problem. This is number 9, I believe. Yes, it's number 9. So it's KSP. Oh, this is a 3-part question. So I might just simply verify this solution for us because we're running out of time here. But maybe I'll do one mock one here. So we have KSP is equal to 6.60 times 10 to the negative 6. PbBr2 is equal to 6.60 times 10 to the negative 6. It's a little cut off, sorry. And it's asking us what is the molar solubility of PbBr2. So let's figure out the chemical equation for that. So we have lead bromide. It's going to dissociate into Pb plus Br2. So we have Pb, we have Pb and Br minus here. Sorry, not Br2, Br minus. And we're going to have 2 bromines here, which means the charge of our lead here is going to be, this will give us a charge of 2+. Because again, the bromine, you can think of the reverse crisscross method. Br2 is the subscript for 2 belongs to the charge of Pb, so it's going to be 2+. And to balance it, we just simply put a 2 for Br. So this is good. So we have X, and we have 2X here. So we can say the KSP is equal to the concentration of Pb2+ times our concentration of Br minus to the power of 2. So we're going to have, this is X times 2X squared, which is going to give us 4x cubed, right? Because we have X and then we have 4x squared. This gives us 4x cubed is equal to the KSP, which is 6.60 times 10 to the negative 6. And we're simply isolating for X, right? So let's divide both sides by 4. So we have 1.65 times 10 to the negative 6 equals x cubed. We can simply cube root both sides to get our answer here. So X, our molar solubility is 0.0118 moles per liter. And this is our molar solubility for this problem. And as again, you can see S is also equivalent to this. So this solution here is correct. And then for the other two problems, I'm just going to simply look at the solution and tell you if it's right or not, just for the sake of time. But it's simply basically the same thing as what we're doing here, except we're going to add it into KBr and PbNO3 solution. So we're going to add something into our products, into our reactant, sorry, and that might change the coefficients for our products. So let's skip ahead and look at what they're doing for 2. So again, you have it in a molar solution of KBr, potassium bromide, and you know that the concentration of potassium bromide is 0.500 molars, right? Which means you know your molar solubility of Br minus is also 0.500, right? Because KBr dissociates into K plus and Br minus. It's a 1-to-1 ratio, so we have 0.500 as our Br minus, and therefore you can substitute this X value for 0.50 and calculate the molar solubility for our for PbBr2. So this solution is correct. Again, I have S and I have 2S plus 0.5, which is great. When you plug that in here, you have X and you have 2 times 0.5, which will give us give me a second here. You have X times 2x squared here. Sorry. So you have 2 plus 0.5, 2s plus 0.5, and then I'll solve algebraically for s here, and this will give us 2.64 times 10 to the negative 5. So this solution is also correct. And finally, for part 3, you have PbBr2 in a concentration of, in a lead nitrate concentration of 0.50. So what you're doing here first here is you're going to write out the chemical reaction for lead nitrate. You're going to see that it dissociates into lead and also the nitrate ion, and you're going to realize it's a 1-to-2 ratio because lead is going to have Pb2 plus is going to equal 0.50 because again you have lead, which is Pb2 plus, and we have NO3 minus. So it's also a 1-to-1 ratio. Sorry about that. Not 1-to-2. It's a 1-to-1 ratio. I'll mix that with my charges here. So you're going to have the concentration of lead as also 0.500, and you're going to plug that in for your molar solubility for Pb2 plus, which is going to be X here, and you're simply calculating you're algebraically isolating this 2x here, and you're going to get 1.82 times 10 to the negative 3. So the solution is correct. Again, the algebra works out here, the logic works out. So I'm going to say the solution is correct. Again, thank you so much for watching this stream. I unfortunately didn't get to my last question of the day for the sake of time, just because that question was very, very long, but it's totally fine. Again, my name is Joey. I'm currently a chemistry teacher. I stream math on Mondays and chemistry on Wednesdays. However, I believe that this is going to be my last stream with OneClass here. So this year, I have one stream coming up in about an hour, which will be the last stream for chemistry for me as well at OneClass. So you can stay tuned for that. Again, thank you so much for watching the stream. Have a great day. Stay safe, stay healthy, and have a great day. Take care.